Alright, so welcome to our next video. So we're going to continue with what we were doing in the previous video where we developed the idea of a sum of products, but we're going to look at what we can consider a dual to that, something called a product of sums. Now, if you've done KVL, KCL in CSE 120, those are dual processes to each other. They're really the same process, but they usually feel different to people who learn them. For most people, KCL feels very different from KVL. So product of sums, or POS, is very similar to sum of products. In fact, it's exactly the same process. But most likely, one of these will feel more natural to you. For most people, sum of products feels very sort of natural and logical, and product of sums seems kind of unusual. So let's see how this works. Let's imagine a truth table, and we've got some places where we want our output to be a 1, some places we want our output to be a 0. Alright, so with sum of products, what we did was we looked at all the rows where we wanted a 1, and we said let's find a combination of A, B, C, or their inverses that gives us a 1 in this case, or this case, or this case, or this case, or this case, and we ORed them together. For product of sums, instead, we're going to look at the situations where we want our output to be a 0, and then we're going to AND each of those. So this is the same approach that we followed for sum of products. We're picking out particular terms from our truth table, finding expressions, and combining those. But this is going to be kind of a backwards version of that, or an inverted version, if you like. So let's find an expression which is 0 when A, B, and C are all 0. And the expression here would be simply A or B or C. And if we're in any other row, this expression is going to be a 1, right? Because in any other row, either C or B or A, or maybe multiple of these variables will be 1, this will be 1. But in this first row, this OR expression, this sum, will be exactly 0. In this fifth row, here's an expression which will be exactly 0. And in this, next to the last row, the seventh row, here's an OR expression, a sum expression, which will be 0. So if we're in any other row, then either this will be a 1, or this will be a 1, or this will be a 1. So if we're in this first row, this is a 0. If we're in this row, this is a 0. If we're in this row, this is a 0. If we're not in one of these 3 rows, all 3 of these expressions will be a 1. So if we take their product as follows, A or B or C, ANDed with A bar or B or C, ANDed with A bar or B bar or C, this expression for X gives us exactly this truth table. And so it's again, it's a dual to the sum of products that we developed in the previous video, but this is a product of sums. We're multiplying or ANDing a bunch of expressions together, and each of those expressions is a sum. It's a logical OR of variables. And we can reason through it by, looking at a particular row and saying, okay, so if A bar or B or C, if we're in this row, all of those will be 0, this will be 0. But once we've thought through that once, we can find a rule for writing this down from the truth table. And the rule is, look at all the places where we have a 0 and write down some combination of A or B or C. But here the rule is, if our variable has a 0, we leave the variable without a bar on top. If the variable is a 1, we put a bar on top. So this row corresponds to A bar or B bar or C. And we do that for each of these places where we have a 0, and then we take the product of those, we AND them together. That's our POS expression. And this is, the standard or canonical form. so it's the full form. But time and again we'll be doing this, and so we can come up with a more succinct way of writing this. So if this is our truth table, and here's our inputs A, B, C, and here's our output X of A, B, C. And I draw this line halfway through just to separate things out, make it easier to line them up. We have a shorthand for this expression, A or B or C. We call it M0, which we call a max term. And so M0 means A or B or C. M1 means A or B or C bar. M2 is A or B bar or C, and so on and so forth. So for each of these, M6, put a bar on top of any variable where you have a 1, and don't put a bar on top where you have a 0. So there's no bar here. This is just an A. And so on. And so if we have our truth table where we wanted to have a 0 in exactly these positions, we could simply have written X of A, B, C equals max term 0 ANDed with max term 4 ANDed with max term 6. And that's called compact form. And we can also write this even more compactly by using a product symbol instead of a sigma to say we're going to multiply a bunch of terms together, and we can just list the index of the max term. So product 0, 4, 6 means this, which means this, which means that. So we can take this whole truth table and reduce it to just this product of sums representation. And we can play around with this, and you'll see this in some of the exercises. For example, if I also look at X of A, B, C as a sum of products, I would look at the terms where there's a 1, and I would see that this was min term 1 plus min term 2 plus min term 3 plus min term 5 plus min term 7. Or in a even more succinct form, I could say it's the sum of 1, 2, 3, 5, 7. And you notice the elements in the product term are exactly the elements that are not in the sum term, and vice versa. And we can convince ourselves that's true by looking at De Morgan's theorem and expanding some expressions. De Morgan's theorem, if you don't remember, basically says this. That's De Morgan's theorem. And it's a way to switch between products and sums and products. And so we can work with that in some of the exercises and see what exactly the connection is and why we're seeing this behavior of, you know, the product of 0, 4, 6 or the sum of the other min terms give us the same equation. All right, so that's product of sums, and anything we can do with sum of products we can do with product of sums. They really go back and forth. All right, so the next thing I want to talk about is simplifying these truth tables. So let's start with 3 input variables. And let me make a truth table like this. And we'll stick with sum of products for now. So if I write this out as a sum of min terms products, This third row corresponds to A bar B C bar, and this fourth row is A bar B C. So there's an expression for x. Well, if we think back when we talked about identities, we saw that we could distribute a multiplication over an addition. We can reverse that and factor things out. We could rewrite this as A bar multiplied by BC bar or BC. And that's potentially a simpler circuit to implement, but we can actually make an even simpler circuit by factoring out this A bar B, and we can say x equals A bar B times C bar or C. And if we were to multiply this, this would be A bar B C bar, that's that term, ORed with A bar B C, there's that term. So we can factor out the A bar B and write our equation for x like this, but this is a really interesting expression. C bar or C. If you think back, we had an identity saying that this is exactly equal to 1. Right? If we write a table for C, C is either 0, 1, C bar is a 1, 0, C bar or C, well, C bar or C is 1, C bar or C is 1. So this expression is always exactly 1. And we had another identity which said if we AND something with 1, that doesn't change the value. So x is actually just A bar B. It's a single AND gate with only 2 inputs, which is a lot easier to build than 2 AND gates with 3 inputs plus a 2-input OR gate. So we can sometimes simplify our truth tables. And what made it possible to do the simplification was the fact that these 2 rows are exactly the same input variables except for this variable C. And the way we can think of this is if A is 0 and B is 1, the value of C doesn't matter. Could be a 0 or a 1, our output is still going to be 1. So we can ignore the value of C in this case where A is a 0 and B is a 1, which is what this expression is capturing. But there's other simplifications we could make. Here's another expression where y is equal to A bar, B bar, C bar, or A, B bar, C bar. And in this case, we can factor out this B bar, C bar. To look like this, and this becomes a 1, and 1 ANDed with B bar, C bar is just B bar, C bar. So there's another simplification. But since these aren't adjacent to each other in this truth table, it may not be as obvious that, you know, as long as B and C are 0, the value of A doesn't matter. So there's a trick we can use. It's a visual graphical trick we can use. It's called a K-map. K is for the name Carnot. And this is a way we can relatively easily find a simpler version of a truth table. So the way we do this, let me start with one of these truth tables over here. Suppose we have ABC. And let's look at our variable y. So to do a K-map, we begin with the truth table, and we look at how many rows we have, and we draw a rectangular shape. For something with 8 rows, we're going to draw either a 2x4 or a 4x2 rectangle. Doesn't matter which way we go. So I'll do a 4x2. And I'm going to have 2 variables coming along here, so I might pick A and B to go along the vertical, and I might pick C to go along the horizontal. And we list all the possible values of these variables. So C is either a 0 or a 1. AB we know could be 0, 0, 0, 1, 1, 0, 1, 1. We have to write this in a different order though. So with truth tables, we always want to write things in this particular order. But with K-maps, when we have two variables, we write them in this order. We go from 0, 0 to 0, 1, and then we jump to 1, 1, and then down to 1, 0. And that's super important. If we flip these, our K-map doesn't work. The goal is that when we move from one box to an adjacent box, exactly one variable changes value. So from here to here, A changes from a 0 to a 1. From here to here, B changes from a 1 to a 0. From here to here, C changes from 0 to 1. Alright, now we fill in our truth table values, and we generally only fill in the ones. So I should have a 1 where A, B, and C are all 0, that's right here. And I should have a 1 where A and B are 1 and 0, and C is a 0. That's right here. Alright, so we fill in the ones. The next thing we do is we try to cover these ones with squares or rectangles. And our squares or rectangles can be 1 by 1, 1 by 2, 1 by 4, 2 by 1, 2 by 2, 2 by 4, 4 by 1, 4 by 2, or 4 by 4. I probably missed a few. But the sides of our rectangles have to be either 1, 2, or 4. And we can also wrap edges. So I'm going to draw a 1 by 2 rectangle that covers these two squares. And that's totally legal. And let me just show you some other K-maps and how we might cover our ones. So we'll just do some examples. So suppose we've taken our truth table and we've copied it over to, in this case, a 4 by 4 K-map. And suppose we have ones like this. Well, we can cover these two rectangles like that. We could cover these two with a rectangle like that. And we need to cover this one. Well, we could do it with a little 1 by 1, but we can also do it with a 2 by 1. And so here's some rules. Cover all ones. We can cover more than once, but we have to cover each one at least one time. And larger rectangles and fewer rectangles gives us a better situation. And all our rectangles have to have sides that are either 1, 2, or 4. We can't have like a 3 by 2, for example. So this would be a good covering for this pattern of ones. For this pattern of ones, we could cover all 4 of these with a single 2 by 2 rectangle. We need to cover this one right here. We could either use a 2 by 1 like that or a 2 by 1 like this. Either way, this is going to be left uncovered, but we can cover this with a broken rectangle that wraps. And so now we can cover this either with a rectangle like that or a rectangle like this. It's not going to make any difference. If we had a map like this, we can actually wrap this on all 4 sides and make a 2 by 2 rectangle that looks like that. And then here's a really horrible K-map. And the only way we can cover all of the ones is with a bunch of 1 by 1 rectangles. And there's really no way we can get a bigger rectangle because we can only cover the ones. Right, the boxes we haven't filled in, those are zeros. We're not allowed to cover those. So that's an example of how we do these coverings. So the next topic is what do we do with these coverings? How do we turn these into equations? Alright, so on to this question of how we write equations from a covering of a K-map. So it's similar to how we write equations directly from the truth table. We basically look at the rectangles that we drew. So in this case, we had a split rectangle. It included these two rows and this column. So our goal is to look at every square in our rectangle and ask what happens to each of these variables in there. For example, in both of these squares, the letter C has to be a 0. And in both of these squares, the variable B has to be a 0. But if we look across these two squares, A could be a 0 or a 1. And so we say A we don't care about. So we write a dash to mean don't care. So how do we write an equation which requires that B equals 1 and B equals 0 and C equals 0, but we don't care about A? Well, that's just B bar ended with C bar. Right? So as long as B and C are both 0, this expression will be 1. And in any other case, if either of these is a 1, then this expression will be a 0. So this expression, this product term, corresponds to that rectangle. And so here we would write the equation y equals B bar C bar, and we would be done. And we can double check that with our original truth table. If B and C are both 0, we're either in this first row, y is a 1, or this fifth row, y is a 1. And if B and C are not both 0, we're in one of these other rows, and in all of those, y is a 0. So this is a good minimized equation for this truth table. So now let's just look at some examples of other coverings of K-maps and see what the equations look like. So I'm not going to draw the truth table because that's 16 rows, but suppose we've drawn the truth table and we filled in our K-map with something that looks like this. So I'm going to put AB over here and CD over here, and we're going to use this funny ordering for labeling each row, where we go from 0, 1 to 1, 1, and same thing going across. And I don't know, let's just suppose we've got some entries like this. Alright, so there's a hypothetical covering of a filling in of our K-map with ones. So let's cover this with rectangles first of all. And it helps to start with kind of the outliers. Like this one in a corner is all by itself, right? There's nothing else next to it except for this one. So to get the best covering for this upper right corner, we're definitely going to want to make a 2 by 1. And once we do that, we've also covered this one. So we can forget about those for now. Let's look at this one over here on the side, and how can we cover that? Well, we could do a 1 by 2 like that, and that leaves us with these two ones that we still need to cover. Well, we can cover them with a single square, but we could also cover them with a 2 by 1, and in this case a 1 by 2. Now this one in the middle, this is covered 3 different times. Totally okay, right? We are allowed to cover more than once, but we have to cover every one at least one time, and we can't cover any of these empty squares which are zeros. We don't draw the zeros just because it would make the diagram more cluttered. So now we're ready to write equations. So let's look at this upper right 2 down 1 across rectangle, and if we look at the value of A is equal to 0. If we look at the value of B could be a 0, 1, so it's a don't care. If we look at the value of C, that's a 1, and we look at the value of D, that's a 0. So, when I've written this is like C is a 1, D is a 0. Here C is a 1, D is a 1. Here C is a 0, D is a 1. So each of these, the first digit corresponds to C, the second to D. So in this rectangle, C is a 1 in both of those boxes, D is a 0. So here's the values for our input variables in this box. And so we can write that as A bar, C, D bar. And that's all we've got to do. So once you've done this a few times, you can stop writing these intermediate steps. I'll do this one more time. I'll look at this 1 by 2 and observe that A is equal to 1, B is equal to 1, C here and here is a 0, but in this box D is a 0, over here D is a 1, so D is a don't care, and so this corresponds to A, B, C bar. And then this rectangle over here, this 1 down 2 across, let's just write it by inspection. A is a 1, B is a 1. C could be a 0 or a 1, so it doesn't matter, but D has to be a 1. And then this 2 high, 1 across box looks like A could be a 0 or 1, so it doesn't matter. B has to be a 1, C has to be a 0, D has to be a 1. And so our output expression would be B, C bar, D, or A bar, C, D bar, or A, B, D, or A, B, C bar. That's all there is to it. Now, if we make our K-map, and suppose we have, a 1 sitting here and a 1 sitting here. The only way we can cover this is with these 1 by 1 rectangles. And if we look at this rectangle right here, what is the equation corresponding to that rectangle? Well, A has to be a 1, B has to be a 0, C is a 1, D is a 0. And if we look at this term, A is a 0, B is a 1, C is a 0, and D is a 1. And if we OR those together, we should get an equation for the truth table corresponding to this. Well, this is exactly what we would get if we just did a straight sum of products directly from the truth table. We would write down these min terms corresponding to those two positions in the truth table, and we would find this is min term 5, and this is min term 12. So in the case where we don't have ones next to each other that we can cover with a bigger rectangle, this just gives us a standard sum of products. But if we had, for example, ones over here, we could cover that whole area with a rectangle. And in this rectangle, we would say, okay, A has to be a 1, B could be a 0 or a 1, doesn't matter. C has got to be a 1, and D can be a 1 or a 0, doesn't matter. So now we've got a single product term with only 2 variables, so a 2-input AND gate to take care of all of those ones. And so this is why bigger rectangles are better. The bigger your rectangle, the fewer number of variables you have. If we had ones in here, and we could cover this whole thing with this 8 square rectangle, we could say A can be a 0 or a 1, B can be a 0 or a 1, those don't matter. C has to be a 1 in both of these, but D can be a 1 or a 0. The expression for this set of ones is just C. And that makes sense, right? If C is 0, then we're in one of these squares, which is not, covered by this rectangle. If C is 1, we're in one of these 8 squares, all of which we want to have an output value of 1. So C is the, product term, single variable, corresponding to those 8 ones. And in the best possible case, where all of these squares were a 1, we can cover the whole thing with a 4 by 4, and none of our variables matter. Doesn't matter whether A is a 0 or 1, B is a 0 or 1, C is a 0 or 1, or D is a 0 or a 1. Doesn't change the fact. So we have no A, B, C's, or D's in our expression for this. In this case, our expression would just be a 1. And in the case where all of these were 0, we would have nothing drawn in. There'd be no rectangles we could make, And without rectangles, again, we have no expressions involving A, B, C, or D, but our equation would simply be 0. So those are the two pathologies. All right, so a few more things to extend on that, and then we'll summarize how we make K-maps in a set of steps, and then we'll go on and we'll take a look at product of sums. And product of sums are very straightforward once you know how to do an SOP with a K-map. All right, so the last case we really need to talk about is the business of don't cares. And don't cares are literally values in our truth table where we do not care whether they're a 0 or a 1. So let me show you an example. So we'll fill out our 16-row truth table. And I'll split this in groups of 4 just for clarity. And again, after you've written a few of these, you get pretty good at filling them in without thinking too hard, or possibly while talking while you fill them. So there's 16 possibilities, and suppose we want our outputs to look like this. And suppose those are the only requirements for our circuit that generates X. It's got to generate these 12 values for these 12 sets of inputs. And for whatever reason, we know we're never going to put in inputs corresponding to these 4 values. Well, if we're building a circuit and we never expect the person to, set A, B, C, D equal to this, we don't care if the output's a 1 or a 0. So we can mark these with a dash. And the dash means we don't care. So this is a don't care. All right, and we can take advantage of those don't cares when we make our K-map. Because if we're going to allow this to be either a 1 or a 0, chances are that's going to simplify our life. So let's make a K-map from this truth table, and let's see how we use these don't cares. So as usual, I'll put AB on the left and CD going across on the top. And then let's fill in the entries from our truth table. So A, B, C, D are all 0. That's this number right here, this box. 0, 0, 1, 0. That's this box right here. 0, 0, 0, 1, 1, 0. That's right here. That's this one right here. And this one, 0, 1, 1, 1, 0, 1, 1, 1. It's right here. And after you do this enough, you'll find a pattern, right? If we just read down our truth table from top to bottom, and it's written in this order with the variables in this order, and my A, B, C, D are written in this order, you'll find there's a pattern, right? We put the rows from here into our truth table in the following order. There, there, jump down and do those, and then do those. So when you discover that pattern, you're welcome to use it, but I wouldn't try to memorize it, right? I would work from the truth table and say, oh, 1, 0, 0, 0, that's 1, 0, 0, 0, that goes right here. And this next row, 1, 0, 0, 1, 1, 0, 0, 1, that goes right here. But eventually, we find this pattern. And now these last 4 entries, these don't cares, these all go in this row. And the fact that it's a dash means it could be a 1 or a 0, either is legal. Well, if it's a 1, right, if we want to generate a 1 in this box, we've got to cover that box with a rectangle. But if we're going to generate a 0 here, we don't have to cover it. So these dashes become optional covers. We can choose to cover them or not cover them, whatever makes our life easiest. Well, this is a good setup, right? So we've got 4 ones right here, but we could cover that by, a 1 by 4, but we can also pick up these dashes and say, hey, let's treat those as 1s, And there's a big 2x4 rectangle that's going to give us a single expression. So that's a good cover. Here's a pair of ones, and we could cover, you know, that with a 1x2. We can't really pick up that extra one, but we could also pick up these dashes. So there's a 2x2, that's good. And this one over here, we can pick it up with that one. We could pick up this one and make a box there, but we can't pick up this. But this is that split rectangle that we mentioned, where we can think of a 2x2 rectangle that looks like this. So let's write equations. This 2x4 rectangle, A has got to be a 1, B can be a 1 or a 0, C can be a 0 or a 1, D can be a 0 or a 1. So this is just the expression A. And this 2x2, A can be a 0 or a 1, B is a 1, C is a 1 in all four of those boxes, and D changes, so we don't care about D. And then this split up rectangle, this one can be tricky. Well, here A is a 0, here A is a 1, so A doesn't matter. But all four of those, B is a 0, so we need B. And C is a 0 here and a 1 here, so C doesn't matter. But D is a 0 here and here, so D definitely matters. So there's an expression for that 2x2 rectangle, which has been, you know, sort of exploded and split into four pieces. And so our equation would be x equals A or BC or B bar D bar. And that's our simplified expression for this original truth table. All right, we can double check and make sure that this is actually correct. Let's make a column first of all for B bar D bar. And so B bar D bar is 1 exactly when B is 0 and D is 0. So all of these, B is a 1. B is 0, D is 0, every other row here. And all of these, B is a 1. And then we can make a column for BC. And so when are BC both 1? Well, they're not both 1 here. They are both 1 down here. They're not both 1 in any of these, but they're both 1 right here. And we can rewrite A. And A is 0 in the top 8 entries and 1 in the bottom 8 entries. And then we can make a column for this expression by just ORing the three of these together. Well, that gives us a 1, 0, 1, 0, 0, 0. Something went wrong here. 1, 1, 1, 1, 1, 1, 1, 1. So what went wrong here? B bar, D bar. Sorry, right here. B bar, D bar. Oh, BC is a 1 here. Right, B and C are a 1, so that's a 1. So yeah, this expression matches our desired value for x exactly. You notice we happen to fill in all of these dashes with 1. That might or might not happen. It could be that some of them are 1s, some of them are 0s. So being able to use these dashes selectively, that's an advantage when we're trying to come up with a cover for a K-map. So that's the business with don't cares. And if we wanted to write an expression for this, we can write this in compact form, like x equals sum, and we can list the min terms where we want a 1, so 0, 2, 6, 7, 8, 9, 10, 11. And then we put this extra thing here, we say plus MD 12, 13, 14, 15. And this plus MD means these are don't cares. So if we want to express a truth table in compact form, we can do it, in the usual way. Here's the product terms that we're summing together, but we're also adding in these optional min terms 12 through 15, but they're optional. They can be treated as ones or zeros. All right. One final comment. This business of splitting these rectangles is not as freaky as it might seem. This has to do with the fact that there's different ways we could draw this K-map, right? We happen to put C before D, but if we had put D before C, these two boxes would have been right next to each other. So we can imagine, for example, continuing this K-map with a second copy, where we put 0, 0, 0, 1, 1, 1, 1, 0, and we can reproduce each of these rows on top. So we'd have our 1 and a 1 and a pair of 1s over here, and some dashes, and a 1, 1, 1, 1 down here. And as soon as we do this, we see immediately, hey, we've got a nice covering right here of a 2x1 rectangle. And then if we go ahead and we reproduce our K-map one more time on the bottom, over there and over there, so we extend this, and so we've got 0, 0, 0, 1, 1, 1, 1, 0. Well, we can reproduce this K-map down here. And reproduce this one. And now it immediately jumps out to us, hey, we've got a 2x2 rectangle we can use to cover those ones right there. And so that's all we're doing when we allow this wraparound, this sort of asteroids model where we can go from one edge to the other. We're acknowledging the fact that, hey, if we had ordered these variables differently, we might have ended up with a situation like this where these would be next to each other or these would be next to each other. And it's visually the same as, making multiple copies of this K-map and then looking for covers in those extended copies. So that's all that's going on with the wrapping on the edges. All right, so let's do a quick synopsis of the rules for making K-maps. All right, so quick synopsis of the rules for filling in a K-map. First rule is copy the ones from your truth table into the squares of the K-map. So, draw your rectangles, label the edges, put in the values for each variable, then copy the ones from the truth table to the K-map. Copy the don't cares as dashes, ignore the zeros. Right, we're only going to copy the ones and the don't cares because that's all we're going to try to cover. And then try to cover the ones with rectangles. And you're allowed to either cover or not cover the dashes. You can cover some of them. You can cover none or all of them, whatever works best for you. You have to cover all the ones. You're allowed to cover them more than once, but you have to cover them at least once. You're not allowed to cover any of the zeros, the empty boxes. When you're covering, you prefer to use larger rectangles and you prefer to use fewer rectangles. Fewer rectangles will be fewer product terms. Larger rectangles make smaller product terms. Each side of the rectangle has to be 1, 2, or 4 in length. You can't have, say, a 1x3 or a 2x3 rectangle. It's got to be 1x2, 2x4, 2x2, and so on. And you're allowed to wrap around the edges, so you can break your rectangles up and, pretend that one edge is connected to the other. And then after you've finished writing in your rectangles, you can write equations, and the equations are based on which variables do not change inside the rectangle. And when you're doing all of this, pay attention to the ordering. Remember that as you go down an edge or across the top, your order is 0, 0, 0, 1, 1, 1, 1, 0, not the usual binary ordering that we're used to. All right, so that's basically all we need for sum of products. Let's do a quick look at one pathological case that we've touched on before, which is this business of exclusive ORs. And if we have an XOR, it turns out to be something like this. It's this checkerboard pattern, right? So an exclusive OR, if we take A XOR B, that would give us a 1. XOR 0 is still a 1. XOR 0 is a 1. We've got a 1 right there. But it's basically every other square gets filled in. And no matter how clever we are, and the only way to cover this is with 8 1x1 rectangles. And that ends up just being a traditional sum of products, where we'd have x equal to, in this case, min term 1 plus min term 3 plus min term 4 plus min term 6. And it's a horrible expression. We end up with 8 product terms. Each of them is a 4 input AND gate, and then we need an 8 input OR gate. But this is also just an exclusive OR. This is A XOR B, XOR C, XOR D. So in some cases, you may find part of your K-map contains a checkerboard pattern, rather than just resigning yourself to these big, long expressions where we have these 1x1 coverings. Take a look at this part and see if you can find a way to cover this part of your K-map with an exclusive OR. Right? So that's a trial and error kind of thing. But that's potentially going to save you some complexity in your equations and thus your circuits. And this is going to come up when we talk about adders, because adding circuits usually involves exclusive ORs. All right, so how does all of this map to a product of sums? Well, it's pretty much the same business, with just a few differences. So suppose we have our equation. Well, we're going to copy our zeros into our K-map. And we'll also copy our don't cares. So suppose we copy our zeros, and this is what our K-map looks like. We use the same rules for covering. So there's an optimal cover. And we write an expression, but it's going to be a sum expression corresponding to this box. So let's go back to our original development. A doesn't care. B has to be a 1. C is a 0 or a 1, so C doesn't matter. D has to be a 1. So that describes this box. This box up here, A has to be a 0, B can be a 0 or a 1, C has to be a 1, and D has to be a 0. All right, so if B has to be a 1 and D has to be a 1, what is the sum term corresponding to that? Well, remember the idea is we take these variables and we add them together, we OR them. And if the variable is supposed to be a 1, we put a bar on top. And so up here, I didn't write in B, but B was a don't care. So this box up here, we're going to have A, C, and D. If the variable is a 0, we leave it as is. If the variable is a 1, we complement it. And then our output expression would be the product of these sum terms. So we'd have B bar or D bar ANDed with this expression, A or C bar or D. And that would be a product of sums corresponding to the truth table that gave us this K-map. So we do the same procedure as when we're doing a sum of products. We copy from our truth table, but we copy zeros instead of ones. We cover our zeros instead of ones, but it's the same covering rules, the same goals, the same wraparound on the edges, the same treatment of don't cares. And then we write an equation corresponding to each rectangle, but this time it's a product term. And it looks like a simplified version of a max term. And then we take the product of all of those sum terms we wrote, and that's that's the minimized equation corresponding to the original truth table. All right, so we'll do lots of practice problems on this in the problem set today.